Welcome back. In this lesson we are going to study parameterized curves, and on first sight this may seem to be somewhat disconnected from the process of integration and from the process of calculus in general, but you'll see soon how this is going to be a useful tool in going forward with things like line integrals. So consider an airplane in the sky. So imagine we mark a dot on that plane, keep track of it over time t. Then x equals f of t, y equals g of t, z equals h of t, where x, y, z is the position of that dot relative to the core of Earth. That is to say, the x, y, z triple changes as time changes. We can think of these three quantities as being dictated by some function of time. So we've seen this before when we've thought about the chain rule, where each of these three variables, maybe not like this, but all three of these variables will depend on some parameter t. It doesn't have to be time, but it typically is. For example, a particle moving in space, obviously as time passes, its position changes. So if we imagine this particle here, well, this particle could actually be traveling, and 1 second later could be in a different position in that three-dimensional space. So each of these three things, notice, is a function of t. We don't give it the same name. They can't all be f of t, otherwise they would all behave the same way, and we don't want to limit ourselves to that. So let's go ahead and take a look at an example. We're going to represent the position of a point as a vector. Vector r stands for position. Not sure why, just usually physicists use that. And the position depends on t, on a value of time. Suppose that at time 0, the position of the point is 1, 2. So that is in two-dimensional space. Right now we're just going to focus on 2 dimensions for a moment. And that r of t, the position of the particle at time t, is its x component will change by the function 1 plus 2t, and its y component will change by the function 2 plus 2t. What is happening to x and y after each additional unit of t? So we'll do this two ways. One we'll actually simulate this and see what happens. But let's go ahead and think about what this might look like graphically. So we know that this starts at the point 1, 2. Now you can think about that as a vector extending from the origin to that point, and think about that arrow as basically having its only job is to point at where the particle is. So that line right there, that line segment, does nothing more than just points from the origin to where that particle is located. So you can imagine that if that point were somewhere way out here, that this arrow would always just try to tell us, hey, it's over here. That's its only purpose. But when we think about vectors, we can also just think about the corresponding ordered pair. Now, if I start to look at the value of t and the value of r of t, at time 0, we know that the position of the point is 1, 2. Now, 1 second later, 1 plus 2 times 1 is 3, and 2 plus 2 times 1 is 4. So that particle is no longer at 1, 2. It's now at the position 3, 4. So it has moved over here. Notice that its x component has changed by 2 units. Its y component has changed by 2 units, but of course it didn't take that path right there. It did not go in an L shape, because we could also plug in 1/2 for t, and we could see that the particle would be somewhere halfway in between those 2 points. And so 1 second after that, plugging in 2 for t, we would get 5, and here we would get 6. So now the particle is at the point 4, 5, 1, 2, 3, 4, 5, 6. So it is now here. And so from this observation, we might say, well, the particle is going to move in a linear fashion. I'll use a different color here. It'll move in a linear fashion along this line. So basically, that particle is going to move out into space in that direction as long as time continues to pass. One cool thing we can do here is we can actually create a Desmos simulation of this to see how this works. So let's go ahead and do that. So here what I'm going to do to simulate this is I'm going to put in the slider for t. And so I'll start off just by typing in t equals 0. And that says, well, what do you want to be the boundaries for t? So we're going to always start at time 0. You could say that t is not really time, and we can start it at -2, but starting it at 0 kind of makes intuitive sense. And maybe we'll look at this for 5 seconds, and I'll just go ahead and press enter at that point. So right now the slider doesn't really do anything, it just changes the value of t. And I'm going to define 2 functions here, one for the x position of a point. So I will call this xp, so that's the x component of my position, or maybe, you know what, better yet, let's call it x sub r. That way it matches our vector name. And we know that this is equal to 1 plus 2 t. And we know that the y of the position is equal to 2 plus 2t. And so right now you could see that because t is 0, xr and yr are the positions 1 and 2. So I'm just going to create an ordered pair, and I'm just using, this is just a, you can see that this has quotes. When I insert the quotes, this is just a comment. So the ordered pair that I'm going to plot is the ordered pair x sub r, comma y sub r. So that's the starting point of our original point. And now if I were to, let me slow this down a little bit because it's going to go pretty fast, and I only want it to do it once. So if I now press play, watch what happens to the particle. It starts to move in the direction of a straight line, and every second you can see, well, after about 3 seconds, you can see it's at the position 7, 8, which makes sense because if we were going to go back to our table and we plugged in 3 for t, we should get 7 for x, 1 plus 6, and 2 plus 6 will give me the point 7, 8. So again, if I just rewind that, and you can see it's moving kind of slowly just because I reduced the speed of that timer, but it's going to continue going in that linear fashion in that same direction until it hits time 10. And then it's going to stop because well, maybe not. Maybe it's going to continue going. So this particle just moves, and the t-value the t-value controls the x and y positions, and the x and y positions are both functions of time. We could also make this more interesting. What if we said that x sub r is equal to 1 minus 2t? So what would that look like for my slider? So let's go ahead and start this over. Whoops. So with the x component of the position being 1 minus 2t, when t is 0, we still start at the point 1, 2. This negative has no effect yet, but as soon as I press play, we're going to be decreasing that 1 by 2 units for every unit of time that passes. So watch where this point goes when I press play. That's going to go off in the other direction because the x value, as you can see, is actually getting negative since I'm subtracting 2t from it. So I have many ways in which I can control this point. I could actually control it by doing something like let the x position be the sine of t, and let's see what happens at that point. So interesting, huh? The x position is only going to fluctuate between -1 and 1. Now it's going backwards, but it's going to fluctuate between -1 and 1, but you can see the y component is still increasing. So the x component, because it's the sine function, and the sine function is limited between a value of -1 and +1, but the y value isn't limited in that way. You can see that it's equal to 21.24. Again, I could continue to make this interesting and say, well, what if both of these were equal to sine? So let's see what happens to that particle in this case. That's pretty interesting too. Now both the x and y components are just oscillating between -1 and +1. But if I make one of these equal to cosine of t, watch what happens now. So now if I press play, now that particle is just going around in the circle. And we know that that's the case because it's actually the unit circle. The x value, or the sine of an angle, is equal to the x component over 1, and the y value is equal to, cosine of an angle is equal to the y value over 1. In this next example, we have, and these are called parametric because the value of x, y, and z depend upon this parameter that we're calling t. It does not have to represent time, but it's kind of fun to think of it as time. So let's think about what happens here. Here we have a function in 3 dimensions. The x component is the cosine of t, the y component is the sine of t, and the z value is equal to t. So first of all, the z value is just going to continue to increase because as t gets bigger, z is going to get bigger. So if we imagine our three-dimensional space, our three-dimensional space with x, y, and z, then as time passes, the z component is going to get bigger this way. The x component is basically only going to be allowed to oscillate between -1 and +1. The y component is only going to be allowed to oscillate between -1 and +1. So what we should expect is we should expect to see some sort of spiral action because the z value keeps getting bigger, but x and y continue to fluctuate between -1 and 1. Let's think about exactly where this point starts. So one of the important things to have kind of in the back of your mind is the representation of one period of sine and one period of cosine. So if I look at just the x component versus t, it's equal to the cosine function. And cosine function, we know, starts at 1, dips to -1, jumps back up to 1. And that takes 2 pi units of time. So this is 3 pi halves. That's, in terms of degrees, that would be 270 degrees. Here, this is at pi. This is at t equals pi halves. And then back here is at t equals 0. So right underneath this, what I could go ahead and plot is the y component of that same graph over that same interval. So here I'm going to try to keep these in line as best as possible. And I know sine does this, or close enough. And those values of t should be the same. And same thing here. And same thing here. So what I do know is that if I just looked at the x versus y graph, that I could definitely pinpoint where these particles are. So at time pi halves, at time 0, x is at 1 and y is at 0. So that means that we're at the point 1, 0. This is at time 0. Now at time equals pi halves, I see that x becomes 0 and y becomes 1. So now this particle is no longer there. It's now up here at the position 0, 1, and this took pi halves units of time. At pi units of time, so remember what we're plotting here is the x and the y components of this function. Here we see that x is at -1, y is at 0, and so that's this point over here, the point -1, 0. This is at t equals pi. And then at time 3 pi halves, x is at 0, y is at -1. So x is 0, y is -1 is about down here. This is at t equals 3 pi halves. And then at time 2 pi, x makes its way back up to 1, y makes its way back to 0, and so now we're back at this point right here. So of course what we're experiencing is a unit circle that toggles among those 3 points in this direction. So we should see that particle start here at time 0 and go around the circle, and then go around the circle again, and then go around the circle again. Now the z-axis is right here, poking right out at us into the screen, and so actually as time progresses, this creates a spiral action because the z component is getting bigger, but x and y are just moving around this unit circle. that should look pretty cool. Let's go ahead and simulate this and see what it looks like in 3 dimensions. So we're going to go ahead and use this app right here. So here it is. It's a very simple app to use. What we see here is just that 2-dimensional representation of the XY space. And here is that particle in 3 dimensions. So we see that at time 0, x is 1, y is 0, and z is 0 as well, because when you plug in 0 for t, you get a z value of 0. So this point is at the position 1, 0, 0. And if we start to move this slider, first of all, we should note that at about time pi halves, that point makes its way pi halves, which is 3.14 divided by 2. We're pretty close to t equals pi halves. And now that particle has moved circularly, because of course the sine and cosine functions are smooth, they're not jagged. That point now moves to the position 0 in x, 1 in y. But we see here in this graph that that position is moving off the xy plane because the z position is equal to t. So we're actually now at the position 0 for x, 1 for y, 1.55 for t. And if I continue dragging that, we can see that that point continues in the 2-dimensional space around the unit circle, but in 3-dimensional space it's creating this helix, this spiral in 3D. So actually, if I start to move this thing and rotate it and I look down on it, I can see that it creates a perfect circle. It's just when I'm looking at it from the side, it just looks like you took a slinky and you sort of stretched it out. I could also change features of this, like for example, if I doubled the frequency of both of these, I made this 2t, and I made this one 2t, what that does is it just creates 2 revolutions per 2 pi units. So I'll see the same shape, but I'm going to see that helix be much more compressed. It's going to look much more compressed because we're moving around the unit circle twice as fast now. So you can see that it's basically creating the helix, but it's a little bit more compressed than it was when we had a frequency that was half the size. And if I make this 3 times as fast as the original function, then you can see that now it's just going to really rapidly move around the unit circle. And it's going to create a very, now I'm just not moving slow enough, that's why it's looking so barren, but you can see that this creates more oscillations still around the unit circle because we haven't changed anything about the cosine and sine function. Another thing we might ask is what happens if you change the amplitude? Well, if you change the amplitude, and you put this back to 1t, and put this other one back to 1t, and put this position back to 0, and let's say I just doubled the cosine function. Remember, the output of the cosine is -1 or 1 on the min and the max boundaries, so if I double those values, now x is going to oscillate between -2 and +2, and so let's see what effect that has. Now you can see x starts at the position 0, 2, because at time 0, cosine of 0 is 1, but 2 times 1 is 2. And so now we get something that looks elliptical because the x component is varying more widely than the y component. You can see that that still creates a helix-looking thing, but elongated in the x direction. And if I double this, or even triple this, then now I can make y oscillate between -3 and +3, where x is still oscillating between -2 and +2. So we can kind of play around with this. Now things get really interesting when you put these functions out of phase. And what we mean when we say out of phase is we've basically changed their frequencies. For example, if I made this sine of 2t, now I get some really odd behavior that almost looks like an infinity. And the reason that's happening is because now sine is moving from 0 to 1, down to -1, back to 0, twice as fast as it takes the cosine function to move from 1 to 0 to -1 to 0. So basically in the time that cosine takes 2 pi units to complete 1 full revolution, the sine function does it 2 times, and so you get all kinds of interesting behaviors. So feel free to play around with this and experiment, because you'll get some cool effects. So in this next example, we want to find parametric equations for a particle that starts at 0, 3, 0 and moves around a circle as shown in the figure below. Now here, the circle isn't moving around, notice revolving around the z-axis, it's actually revolving around the x-axis. So it's z and y that form the circle, and if we want to model that, first of all, we see that the x component is not changing at all. So the first thing I can say is that x is going to equal 0. Now I want this particle to start at a y value of 0, and then I want it to move counterclockwise. So basically that particle should go to what starts off at 0, 3, 0, should then come down to, let's see, x is still 0. Well, x is always going to be 0 for this particular circle. The y component is now negative 3. And, I'm sorry, the y component is now 0 because we've moved closer to y equals 0, and the z component is now negative 3. And then that particle should move to 0, negative 3, 0, and then back up here to 0, 0, positive 3. So you can see all we really need to focus on is just the y and the z component. We already know how we're going to be able to get that amplitude of 3 units. That's just going to be applying a factor of 3 to our sine or cosine function, to both our sine and cosine functions, because we want y to go from negative 3 to 3 and z to go from negative 3 to 3. But we've got to think about how do we get this to go counterclockwise, because in our previous picture up here, the function went clockwise. So how do I get, really what I'm asking for is I still want this component to approach 0, but I want the vertical component to approach a negative value instead of a positive value. Well, let's think about this. If I take the cosine function as it is, goes from a high to a low, back to its high. And in that same period of time, so this is going to be I want my y component to go from 3 to 0. So 3 to 0. Now my y component is going to go to negative 3 over this half circle. Back up to 0. So back up to this y value here. And now my y value is going to increase back to 3. So to do that, I will use the cosine function, but my y component will be 3 cosine of t. My z component, I have to think about the fact that I want it to go from 0 to negative 3 first. So 0 down to negative 3. And then once the z value goes to negative 3 over the next quarter circle, z will go back to 0. And then z will go up to 1 and then back down to 0. So this almost looks like a negative sine function, right? Because that's the sine function. The negative of a sine function will just reflect it about the horizontal axis, but I want this to be negative 3 and I want this to be positive 3. So if I take negative 3 sine of t, I will be able to model this. And so the position of my particle, if I wrote it as a vector, would be the vector 0, 3 cosine t, and negative 3 sine t. You could also change this frequency. The frequency doesn't have to be what it is. You could double the component, the t component here, and that circle will just revolve faster. It doesn't say how fast this circle needs to oscillate. But let's go ahead and simulate this in our app. So here we said that the x component was going to remain 0. So this guy will be 0. The y component will be, we said 3 times cosine of t. And this will be negative 3 sine of t. So that is what we wanted. We wanted this point to start at the location 0 in the x, 3 in the y, 0 in the z, and let's see what happens now as we start to play this. So it does in fact look like it is moving it around the, revolving around the x-axis, which is coming out directly at us. Now the reason this graph looks kind of funny is because x isn't changing at all, it's just y and z that are both changing. And you can see that we are moving, in fact, around that circle in a counter or in a clockwise fashion. Again, I mentioned that you could change these, make this 2t and make this 2t as well. All that does is makes everything happen twice as fast, but they're still in phase. And you can see now the circle just happens much faster. So whichever one you use, or even cosine and sine of 4t or 10t. There's nothing specified about how fast this particle moves. We're only restricted by the fact that we want it to move around this circle and around the x-axis. So that is one thing that we can do as well. Suppose a particle that starts at the point 2, 1, 0 moves along the vector negative 0.2, negative 0.1, and 0.3. And we want this point to move from the location 2, 1, 0, and we want it to move along the vector negative 0.2, negative 0.1, positive 0.3k per 1 unit of time. So in other words, if we think about what should take place, if we looked at the x, y, and z components as a function of time, at time 0, x, y, and z should be at 2, 1, and 0. So in three-dimensional space, what I should see is if this is x, this is y, and this is z, that the x component should be at 2, the y component should be at 1, and the z component should be at 0. So we should be right at that point right there. And so now as time takes off, we want the x component to decrease by 0.2. So as t becomes 1, we want this to become 2 minus 0.2, which is 1.8, and this to decrease by 0.1, and this to increase by 0.3. So now this point has moved off the xy plane, and it has actually moved a little bit closer to the z-axis because of the fact that the x and y components are now smaller. I won't try to draw that on here because it's going to get kind of convoluted, but what I want to really focus on here when I'm writing a parametric equation is to think about what kind of function models each of the three pieces. Well, if I think about the fact that x is going to decrease by 0.2 as t increases by 1, that's the same thing as saying x is equal to 2 minus 0.2t. So if t becomes 2, now I want this to the original 2 to have decreased by 0.4, and at time 2 this should be at 1.6, and this should be at 0.8, and this at 0.6. So y is going to start at 1 and decrease by 0.1 per unit time. Z is going to start at 0 and increase by 0.3 per unit time. So if I wrote this vector out here, and I wanted to express this as a function of time vector, the x component we just mentioned should be 2 minus 0.2t, y is 1 minus 0.1t, and the z is 0 plus 0.3t. And now if I go over to our model of this, we can say that this is 2 minus 0.2t. The y component is 1 minus 0.1t, and the z component is 0 plus 0.3t. 0 plus 0.3t. And you might be wondering why I'm leaving the 0 there. The reason I can do that is pretty suitable to describe how we separate the initial value of the vector from the variable component of the vector, and it'll just be a good reference point to have. So here you can see where that point A starts off. It starts off at the position 2 units in x, 1 unit in y, 0 in z. And as we start moving that point, you could see that it's moving, the x and y components are approaching the origin, the z component is getting greater and greater and greater, and for this particular example, we see that at time 10, the x and y components are both 0, and the z component has reached 3 because 10 times 0.3 is 3. So you can see that in that case we're moving along that vector starting at the point 2, 1, 0. So that's a real neat thing we can do with these models. Now we've already considered this. We said think about a point x and y. We can think of the point in vector form. So even though it's just a dot, we can always draw a vector from the origin that just tells us where the point is. It's like somebody pointing with their hand saying, look, there's a plane, and using their finger to follow the path of the plane. That's all this vector is doing, is it's just pointing to the current location of x and y. Now if x is a function of t and y is another function of t, then r changes over time, and so we can write it as r of t vector equals the f of t function times I plus the g of t function times j. And remember, all that means is f of t times I is simply the 1, 0 vector, and g of t times I, which is simply the 0, 1 vector. If you now simplify this, this becomes f of t 0 plus 0 g of t, and when you add these together, you just get f of t and g of t, which are just the two functions controlling our x and y components in that vector function. So we can now reparameterize the problem in the parameterization in problem 3 in vector form, where r0 was the position of the particle at time 0. And so we could actually say from above that when we wrote r of t as 1 minus 0.2 minus 0.02t and 1 minus 0.1t, and this one was 0 plus 0.3t, we could actually separate this into two vectors. The first one being 2, 1, 0 minus the variable vector, which contains, or plus, negative 0.2t, negative 0.1t, and 0.3t. So this right here is what we're referring to as r sub 0, or the position at time 0, and that this is the change component. This is going to be called the change in the position as a function of time, and when you add these together, you can really just write the equation in a slightly different way, where your r of t, your position at time t, can be written as your initial position plus the change in your position. And finally, let's look at another problem just to kind of reason through what these things are doing. Are the lines x equals negative 1 plus t, y equals 1 plus 2t, z equals 5 minus t, and x equals 2 plus 2t, y equals 4 plus t, and z equals 3 plus t, are they parallel? Do they intersect? If so, where do they intersect? So to see if they're parallel, first of all, let's break these two things up into their position vectors. So we'll call this r1 of t, and r1 of t I can write as the x component, the y component, and the z component. The second vector here, r sub 2 of t, that I can write as x is 2 plus 2t, y is 4 plus t, and z is 3 plus t. Great, so now I just need to check if they're parallel. Well, if they're parallel, that means every time t increases by 1, x, y, and z should increase by the same amounts. If I think about what that might look like in three-dimensional space, these particles we know are moving along a straight line. So if I saw this, where this vector starting here maybe was moving along that position, but this vector over here was also moving along that same position, the change in x, the change in y, and the change in z are all the same, then I could say they're parallel. But what I notice if I rewrite this first vector, which is its initial position is negative 1, 1, 5, plus t times 1, 2, 1, so those are the coefficients of t, sorry, negative 1, I can see that this that this particle, this guy here, is moving along the vector 1, 2, -1. What position or what vector is this guy moving along? Well, if I do the same thing, it starts off at the position 2, 4, 3, and where it starts is irrelevant to whether the lines are parallel or not. If I do the same thing, break this second vector apart into 2, 1, 1, I can see they're both moving along different vectors. So they're not parallel as they move along different vectors. And so those vectors are, we can call that vector 1, vector 2, and they clearly move along different paths. Every time t increases by 1 here, x increases by 1, y increases by 2, z decreases by 1. But every time t increases by 1 here, x increases by 2, y increases by 1, and z increases by 1. So there's no way these two vectors can be parallel. And lastly, we want to know, will these ever intersect? So how would we solve a problem of whether vectors ever intersect? Well, what I'm really asking for is, if they do intersect, then they should be at the same position at the same time. So R1 of t should equal R2 of t. And I'll put a question mark above there. Do they ever equal each other? Well, I could break this down further and say, well, if they do, then for the same value of time, all the three components should be equal to each other. So in order to solve this, I could figure out, okay, so for the x components, when are they the same? Sorry, I'm having some technical difficulties here. So when are the x components the same? X components same when, well, -1 plus t, whenever that equals 2 plus 2t. And I could figure out when exactly, at what moment in time, the x components are the same. And if I solve this equation, subtract t, subtract 2, I get at t equals -3. Now that by itself is no problem, right? Because it doesn't have to be time, it's just a value of the parameter. But in order for these two vectors to ever intersect, or these two particles to ever collide, I have to make sure that the y components are also the same at exactly the same time. Well, let me check when the y components are the same. So when does 1 plus 2t equal 4 plus t? Is it at the same time? Well, let me see. If I subtract t and then I subtract 1 from both sides here, I get t equals 3. And I can see here that x and y are never simultaneously the same. Are never simultaneously the same. So what does that mean? They never intersect. There's not even a reason why I would need to go on to the z components, because if there's not a single time where both the x and y components are the same, then clearly it doesn't matter what z is, because I want to know, will these two particles ever collide? And they are not going to. Another thing we might want to sometimes do is create a parameterization for a circle of radius 1/2. So that's just going to be scaling our sine and cosines by 1/2. But we want it centered at the point -1, 2. So in order to do that, what I have to think about is, okay, first of all, if I were just to create a parameterization for a circle with a radius of 1/2, I could just say x is 1/2 cosine t. Notice that it doesn't say it has to go counterclockwise or clockwise, so we could just pick the simplest circle we can think of, which we've already worked with, and the 1/2 there will just ensure that this circle has a radius of 1/2. But we know that these components, this is going to fluctuate between -1 and +1, and this is going to fluctuate between -1 and +1. So how do we get it to do that around the point -1, 2? Well, it's as simple as basically adding the initial state vector, which is -1 and +2 over here. If you think about what that does to x when you subtract away 1, well, that's just going to move the center line down to -1 with oscillations of a half that'll look like this. And when you take 1/2 sine of t plus 2, what that's going to do is it's going to shift the center line up 2 units, and now it's just going to oscillate about the point 2 with a amplitude of 1/2. And so the reason I wanted to point this out is because now your position vector can again be written as your initial vector, which is -1, 2, but now your x and y are simply oscillating functions that will cause this to be go from -1 to +1, but because we're adding it to -1, it's always going to shift all the points down, and this guy being 1/2 sine of t will do the same thing. Again, we can do 1/2 cosine 4t as long as we do 1/2 sine of 4t as well. And one other cool problem that I like, find the points at which the line x equals t, y equals 2t, z equals 1 plus t pierces the sphere of radius 10, centered at the origin. So here's a little 3D GeoGebra simulation. I have a slider here starting at t equals 0. The sphere of radius 10 is x squared plus y squared plus z squared equals 10 squared. And here I just have a point that is referencing the current value of t, t for x, 2t for y, 1 plus t for z. So when t is 0, you see that the particle is at the point 0, 0, 1. And as we begin increasing t, we can see that x, y, and z are all three going to go up. And so there goes that particle, and let's see, where is it? It's now outside of the sphere, and that's at time 4.7. So it looks like right somewhere about there, time 3.9, that point breaks through the sphere. And we could also add a little trace component to it. Let's see if we can do this. Show the trace of that point so you can see where it's been. So there it starts at 0, 0, 1, progressively moves its way until it breaks through that sphere. Now you can see many cool applications of this already in terms of how much fun you could have with this type of problem. Now, of course, for us, we want to find this point mathematically. So like 2 examples ago, we'll do a similar process. We're going to ask, when does this vector, which is r of t, which is t, 2t, 1 plus t, when does that break the sphere? So that sphere has the equation x squared plus y squared plus z squared equals 100. Now, in order for this point to touch the sphere, right, every single point along this sphere satisfies the condition that the square of x added to the square of y added to the square of z has to equal 100. Well, that means for me, here, the square of t, which is my x, plus the square of my y, which is plus the square of my z, has to equal 100. And I'm just going to go ahead and do this algebraically here, but we could solve this equation by using Desmos or by using Wolfram alpha. You know what? Actually, we're going to have to solve a quadratic here. So I don't know if that I really am interested in doing that, but let's go ahead and at least expand it out a little bit. So t squared plus 4t squared, and then foiling this out will be t squared plus 2t plus 1 equals 100. And combining like terms, I have 6t squared plus 2t plus 1 equals 100. And now if I want to solve this equation, I can use the quadratic formula by subtracting the 100 over, but we can do it in Desmos as well. Just figure out, when does the parabola exceed 100? And so here I have that function input, and if I scroll down far enough, there are actually 2 points where that happens. One is a negative value of t, which we started at t equals 0, so we're going to ignore that. So at t equals 3.8988, which is pretty consistent with what we came up with here, it took just somewhere between 3 and 4 units. We knew that for sure. So we can say t is about 3.9 is about 3.9 when that happens. So we'll do a lot more with parameterizations. You can model velocity, acceleration, all kinds of cool stuff with this, and that will be in our next lesson. So see you then.